started. Are there any questions I can answer about anything from last time before we start in today on multiple regression? Let me see if I can do this. Any questions at all? No? Okay. Well, we're kind of sitting here at the course now. We're at week 1, 2, 3, 4, multiple regression. 2 more weeks until March break. And the material for the last half of the course I'll be posting relatively soon, week by week. So if you want to get ahead, you can look ahead to that stuff. But today we're going to look at multiple regression. And I put pointers to readings you can do, and a list of topics we're going to cover today. We're going to look at the multiple regression equation and see how it differs from bivariate regression. We're going to talk about the graphical interpretation of a multiple regression. We'll talk about the meaning of the different weights, the different coefficients in the model equation. And we'll talk about a procedure called stepwise regression, which is a way of taking a regression model and pruning it to the most efficient form. And we'll talk about various ways of measuring the performance of an equation, of a regression model, and the assumptions. And that hard to pronounce word will come up again. Heteroscedasticity. Usually say at the beginning of a lecture, but not at the end. All right, why don't we get started then? Multiple regression. So we saw last time the equation for bivariate regression. This is when we're using an independent variable x, plotted here, to try to predict or model a dependent variable that we call y. And the equation looks like this in bivariate regression. Each y observation is equal to an intercept, theta 0, plus a weight, or a slope, theta 1 times x, plus random variation. That's the noise term. And so it's called bivariate regression. The bi refers to 2. There's an independent variable and a dependent variable. There's 2 variables. And that's what it looks like, the red line. So 2 model coefficients, 1 intercept and 1 slope. In multiple regression, it looks a bit freaky, but the equation looks like this. Now we don't just have 1 independent variable x, but we have n of them. Actually, we'll use k. I should change that to n to k. We're going to have k independent variables, x1 through xk. And so now each dependent measure y is predicted by, or is modeled by, 1 intercept. There's still only 1 intercept. But now there's a slope for each x variable. Each x variable has its own slope parameter. So if there's 2 x's, x1 and x2, then there's a beta 1 and a beta 2. If there's 10 independent variables, x1 through x10, then there would be 10 slopes. 1 slope for each x variable. But still only 1 intercept, beta 0. Okay, so I'll fix that and make it a k. But the k refers to the number of independent variables, and the n refers to the number of observations. So if we have 100 observations, then we would have 100 sets of a y variable, and then the value of each x variable. And we would have 100 of those. Okay, any questions about the equation? I don't think it's that big of a deal to jump from that one to that one. We're just adding more x variables, and each x variable gets its own slope. So when there's 1 predictor variable, x, a bivariate regression is still a form of multiple regression in which there's just 1 x variable. When there's 1 predictor variable, x, then the regression model looks like a straight line. Right? Beta 1 plus beta 0 plus beta 1x corresponds to a straight line. Y equals mx plus b. When there's 2 predictors, so So here's an example. Let's say we want to model a car's fuel efficiency in miles per gallon. That's a function of two things, the weight of the car and the car's engine size. So the dependent variable y would be miles per gallon of each car in our data set. The first x variable, x1, would be the car's weight, and the second variable, x2, would be the size of the engine. So now the model would have three coefficients to estimate. Beta 0 will be the intercept. That's the predicted miles per gallon when a car has zero weight and zero engine size. So it's not particularly interesting for us. It's a weird thing to want to know. But mathematically, that's what the intercept corresponds to. It's like in a bivariate regression where the line crosses the y-axis when x is 0. And then the two slopes, beta 1 would be the dependence of, or the slope of, miles per gallon on car weight. How does miles per gallon change when the car's weight changes? And beta 2 would be the dependence of, or the slope of, miles per gallon versus engine size. How much does miles per gallon change when engine size changes? So each slope is attached to each x variable, and the meaning of each slope is how much the dependent variable changes with the unit change in that independent variable. So instead of a scatter plot in 2D with a line, now when we have two dependent variables, we have a 3D plot. We have x1 weight on the x-axis, x2 displacement, which is the engine size, on the y-axis. But now we have the z-axis pointing up, and that's the dependent variable, miles per gallon. So now each point in our data set, each observation, is a point in that 3D space. Each observation, each car in our data set has a engine size and displacement, it has a weight, and it has a miles per gallon measure. And so we can plot it in 3D. This data comes from a built-in data set in R called MT cars, if you want to explore that on your own. Any questions about that plot? That 3D plot? Yeah.
You see the z-axis is the one pointing up, or is that still the y-axis?
That's right. Now the z-axis is this one pointing up, and the x and y are down on the bottom. So if you were kind of floating up here in space, looking straight down at the floor is like the x-y axis in the bivariate regression, and up is the dependent measure. I mean, it doesn't much matter which goes where, in fact. It's just a convention, really. It's a plot. The dependent measure is the one going up.
So we call the dependent one z now?
Sure, you can do that. Yeah. Usually in a 3D plot like this, x and y are on the floor, and z is the one pointing up. Other questions? Yes?
What if you have more than 2 x variables?
That's a great question. Yeah, we'll get to that in a second. We'll get to the issue of more than 2 x variables in a second. So in a bivariate regression, the model corresponded to a straight line through those data points. Now we have a cloud of data points in 3D, and the model corresponds not to a line, but to a plane that travels through those 3D points. And that's what this is supposed to represent, is a plane, a flat plane. It's like if the data were suspended in this room as a cloud of data points, and you had a big sheet of paper, and you wanted to sort of tilt that sheet of paper just in the right way and translate it in just the right position so it went through the data points. Yeah.
Would then, if it's like based on the plane, if it's just like a straight line going down, or if it's more scattered, is that then the spread of the...
Yeah, so you're asking about essentially the error measure of the spread. Yeah, the error measure is still the vertical distance from each data point to the plane. So instead of the data point to a line in bivariate regression, now it would be these vertical lines between each data point and where the line first hits the plane that would define the error. Yeah? Oh, the displacement variable is engine size of each car. So each car has a weight, each car has an engine size, measured as a displacement. Don't ask me more than that about how engines and displacement work. That's the extent of my knowledge. I just get in my car and I press go. That's all I know about cars. So car weight, engine size, and fuel efficiency miles per gallon. So now I have a plane instead of a line. And just like before, the model fit is defined by these residuals, these vertical lines now. The vertical distance of each point to the plane is the residual. And the sum of squares residuals, just like before, corresponds to a measure of the model fit. So how do we interpret these slopes in the context of this plane? If we rotate the view now, so now we have weight going along here on the bottom and miles per gallon, the dependent variable on top. So now we have y going up and down, and we have x1 going left and right. And displacement, we're sort of rotating this view so that displacement goes straight through the screen. And now we're looking at that plane. The slope of that plane now represents that coefficient beta 1. It's the dependence of the dependent variable on changes in the x1 variable. So how much does the dependent variable change if I change the x1 variable by a unit amount? And because displacement is going straight through the screen, we're taking a view that essentially is independent of displacement. And you can see that because the plane has been drawn here by the graphics program using a series of sort of parallel lines going each way. And you can see those lines are the same down here. The slope of this line is the same here, 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 and here. The slope of those lines doesn't change as you move through space in the displacement direction. In other words, the slope, beta 1, is independent of the value of beta 2. Doesn't matter what engine size is. This model estimates a slope of weight versus miles per gallon independent of what displacement is. And we can rotate this view 90 degrees this way, and now weight is going through the screen, and we're plotting x2 on the bottom and y on the top. And now the slope of those lines corresponds to beta 2, the dependence of miles per gallon on x2. And again, that slope is the same no matter what the value of weight is. Okay, so we've got a plane going through 3D points, and the plane has two different slopes. One slope, when we take a view independent of displacement, and we just look at weight versus miles per gallon, that's x1 versus y, and that slope is beta 1. And one view where we're now ignoring x1 and just looking at the dependence of y on x2. And that slope corresponds to beta 2. So it's a model with one intercept and two different slopes. Yeah?
So for like the total number of points that there are in this visualization, like is it the number of points in like displacement and MPG plus in MPG and weight?
No, so the question was, is the number of points in displacement versus MPG different than the number of points in weight versus MPG?
No, like if they both have the same, that's like the number
They
of
both have the
observations
same,
or whatever.
it's just the data.
In the
Yeah.
visualization, like is the total number of points double then?
No, this is just two different ways of visualizing the same data set. Yeah, it's like, just imagine the data as a cloud of points in this room again. And x1 is this way, and x2 is that way towards the door, and z is up. If I just sort of walk in the room and I look at the data from this vantage, I'm looking at x1 versus y, and I'm ignoring x2. I'm kind of looking through the x2 direction. And if I were to walk over here, now I'm looking at x2 versus y, and I'm ignoring x1. I can't really distinguish between different values in x1. And that's all I've done here. It's really to illustrate the idea that this plane has two different slopes. It has a slope that depends on x1, and it has a different slope that depends on x2. And when you plot it in 3D, it's a little hard to see the two slopes. But you can imagine taking a piece of paper that's parallel to the floor. Here. So now there's no slope at all in x1 or x2, right? And if I tilt the paper just this way along the x1 axis, now it has a slope with respect to x1, but still no slope with respect to x2. There's no tilt this way. Right? And if instead I were to tilt the piece of paper just this way, now it has a slope with respect to x2, but no slope with respect to x1. And of course I can tilt it in two ways, up and then to the side, and now it has two slopes. So it has a slope with respect to x1 and a different slope with respect to x2. And so that's all I've done in this visualization. The key idea really is that each theta variable here, theta 1 and theta 2, they correspond to slopes. How the dependent variable varies with each unit change, with the unit change in each independent variable. How the dependent variable changes with the unit change in each independent variable. Okay. What if there's more than two? That's my answer to your question, wherever it was. I don't know. I can't draw in more than 3 dimensions. But that's what you'd have to do. You'd have to have x1, x2, x3, and then where would y go? I don't know. I have no idea. Humans just can't, except for a rare breed of theoretical mathematicians like me, humans can't really visualize in more than 3 dimensions. But the equation is not a big deal, right? The equation for 2 independent variables looks like that. If I wanted to have 3 independent variables, I would simply add plus theta 3 times x3. And that's it. That's the only change I'd have to make. All the math would be the same. The interpretation would be the same. I'd now have 3 slopes instead of 2. I'm now predicting y based on 3 quantities, not just 2 quantities. I could have 10 x variables or 50 x variables, and nothing really changes conceptually. But visualizing it, I don't know how to do that. I guess you can have a 3D data cloud, x1, x2, x3. And then the y variable would be time. The position of those dots could move in time, and forward and backward could be, the y. That doesn't really help me. That's a little trick, but it doesn't really help. Okay, so that's the multiple regression equation. A single dependent variable y, a single intercept, and then pairs of slopes and independent variables, as many as you want. And the idea is we want to predict or model how that y variable changes depending on all of the different x variables. So you might be, if you're a president of a university, you might be interested in modeling how students' grades are predicted by their age, their high school grades, their socioeconomic status, a whole bunch of different things. And you can model that relationship. Actually, a university president would just be interested in money. They wouldn't be interested in grades. Let's be honest. A dean might be interested in how grades are modeled. So, one predictor, bivariate regression, is just a line in 2D space. 2 predictors would be a plane in 3D space, and more than 2 predictors would be I don't know what. Mathematicians call it a manifold in n-dimensional space. So a line turns into a plane, turns into a linear manifold. That's the jargon for a straight-ish, flat-ish kind of thing in more than 3 dimensions. Okay, let's move on and look at an example in R. So there's a package called Palmer Penguins that you can install. There's a web page that describes what it is. It's kind of fun. It's real data. It's measurements for 344 penguins of 3 different species observed on 3 islands in the Palmer Archipelago in Antarctica. So if you I think you might have to install that package Palmer Penguins first. You then do library Palmer Penguins and library Tidyverse. You can take a glimpse of the data set to see what it looks like. So we have 8 different variables for each penguin. The species, the island it was living on, the length of its bill. Its bill is like its beak, so how long its bill is. The depth of its bill, that's kind of how thick it is, up and down. The length of its flipper, how heavy it is, whether it's male or female, and the year that it was measured in. So let's say we wanted to supplement our data set with more penguins, but we decided it's too much of a nuisance to try to get each penguin to stand on a scale and be measured for its body mass. That's just so labor intensive. You have to chase them around, get them to stand still on a scale. It's anyone who has a dog or a cat has taken them to a vet to be weighed. It's a nightmare. So let's say instead you want to develop a model where you could predict the body mass of a penguin based on the length of their flipper, the length of their bill, and the depth of their bill, because those are easier to measure, let's just say. Okay, so what we're going to do is we're going to gather the variables we need using dplyr. We're going to do a plot called GG pairs that's going to give us a first impression visually about how these different variables relate to each other. We're then going to build our multiple regression model using LN. And it's called a full model because it's going to contain all the variables that we think might be interesting for us. We'll check the assumptions of our linear regression model. And then we'll do this stepwise procedure where we refine the model. And refining the model means kicking out the variables that don't really contribute much predictive power. And then we'll interpret the model we have at the end. Okay, so those are the general steps in the multiple regression. Get the variables we need, get a first impression visually, build a model, check the assumptions, refine the model, and then interpret the final refined version. Okay, so let's define a variable called t-data. It's going to be equal to penguins, and then we're going to pipe. We're going to select only the adelaide species of penguin. We're then going to select the columns of data that we want to look at. Body mass, flipper length, bill length, and bill depth. And we'll just forget the other ones like island and year. Then we're going to drop _NA. Drop NA basically excludes any rows of data that contain NA values. And NA values, capital N, capital A, that's how you signify in R that a data point is missing data. Like maybe there was a penguin that you just couldn't get on a scale. And so you have everything else, but you just don't have the body mass. So we want to kick those out because we don't want to have little pieces missing. There is a whole sort of subfield of statistics about how to deal with missing data. Because you can imagine, if you've got a big data set with a lot of variables, and it's sort of sprinkled with isolated missing data points in certain, in one variable at a time. Kicking out all those data points, even though, you might have 9 measurements, but not a 10. Kicking the whole thing out, it's a little wasteful in a way. So there's a whole subfield of stats about how to fill in the holes when you have missing data. We're not going to go into any of that. This is just to tell you that exists. There are ways of dealing with it other than just simply kicking out each observation. But today, we're just going to kick out those observations. And then we'll use glimpse to get a look at the first couple of rows. So here's what we end up with. We have 151 penguins. And for each penguin, we have its body mass, flipper length, build length, and build depth. So a reminder, we want to predict body mass. So that's our y variable. That's our dependent variable. We want to predict it based on these three independent variables. So we're going to have three x's in our equation. One for flipper length, one for fill length, and one for build depth. Okay, so you'll probably first need to install packages ggalley. And once you've done that, you can library ggalley, and then ggpairs, and if you give it the data frame, will generate a nice plot like this, which is basically each variable against each other variable, showing all the data points as a scatter plot. So a series of 2D slices through the data. On the other side, it will show a correlation coefficient of each variable against each other variable. So this is the correlation between fill length and flipper length. This is the correlation between fill depth and body mass, and so on. And then these lines are histogram, basically a smooth version of a histogram that shows you how normal or not each variable is. So the purpose of looking at all of this really is to have a look at how each variable is related to each other variable. In a bivariate regression, plotting a scatter plot is sort of the whole thing, right? You're plotting x versus y, and that's the data you have, and you can get all sorts of information from that. Does it look like a linear relationship? Is there a lot of variability? Are there outliers? When you have multiple x variables, unless you can figure out a way to plot in how many dimensions do you need to plot? If we have one y variable and three x variables, you need a 4-dimensional plot. I don't know, maybe that new VR headset that Apple has can do some kind of 4-dimensional plot. But I don't know how you would do that, how you would look at that data class. So this is kind of an alternative, is instead of trying to look at the whole thing at once, you look at a series of 2D slices through the data. And so the kind of thing we can see, for example, is that body mass versus build depth down here, there seems to be a noisy but maybe linear relationship between body mass and build depth, and maybe also with build length. And what about build length versus build depth? Build length and build depth, maybe not so related, maybe there isn't a tight relationship. And these ones are kind of circular clouds of data, so maybe not a relationship. So you can, and looking at the correlation coefficients, you can also get a sense of what's related to what.